Hello, everybody, and welcome to the encore presentation of GPR for utility locating presented by me, Dan Bigman, founder of LearnGPR.com. And before we get started, I want to ask a few questions to you. Have you ever had a locate occur where the excavators still hit the utilities? Have you ever felt like you would have more business opportunities if you had the right technology in your arsenal, if you had the right tools for the job? Did you know that over 44% of all damaged utilities are gas lines, which are typically made of PVC? So why is that? Why is that? Well, the purpose of today's webinar is to give you some background in ground penetrating radar, because this technology is clearly changing the landscape of how utilities are located today. What we're going to begin with first is a brief overview of ground penetrating radar and how it works. Next, we're going to talk about how deep can it prospect. Then we're going to quickly look at some examples of data from surveys where GPR was used to locate buried utilities. Finally, we're going to compare ground penetrating radar, GPR, to traditional locate equipment and see kind of what the pros and cons are, because what I want you to get out of this is to understand the limitations of GPR, but also its strengths. And then to conclude, I'll take your questions and answers live right here on the webinar to answer anything that you might have. So what I want you to get out of this, right, when you leave this webinar, is I want you to have an understanding of the basics of ground penetrating radar. You will understand how it can be applied in utility locating and when and where it's most effective. And I think you'll agree with me at the end, which is that this technology will be required technology on almost all surveys in the near future. This is not something that's going to happen long-term into the future. It's something that's going to happen in the near future. So to give you a little bit about myself, my background is I got my PhD from the University of Georgia, and I went there for archaeology. And archaeology and utility locating are actually very similar industries. They are both, we're actually, with utility engineering, very similar industries. They're both destructive, right? When you trench down and you excavate out, you destroy what's below the surface. And so what you want to try to do is either document that or preserve it, whether it's archaeological remains or infrastructure. So when I went to graduate school and I understood, at least from my perspective, that what archaeology did was dig, I was absolutely floored in my first semester when I was taking a near-surface geophysics class. And in this near-surface geophysics class, the professor showed me an image. It was an image of a Cherokee, Native American Cherokee house that he and other archaeologists mapped. What was so unique about this experience, though, was that there was no excavation involved. They mapped this entire house, where the walls were, where the hearth was, where the storage pits were, without ever disturbing the ground surface. And from that moment on, I was hooked. I was hooked with remote sensing. And I then spent the next 10 years of my life devoted to understanding this technology and how it can be applied in other domains like utility locating to help preserve past human labor, to help preserve the assets that humanity has developed over centuries, both historical but also more recent, like utilities, like infrastructure. And so since then, I have conducted surveys in forensic cases, archaeological studies, and civil engineering contexts across the country, from the East Coast all the way to California. I have done that. I have been invited to speak to the European Association of Geoscientists and Engineers on my research using ground penetrating radar, and I have and I've been on the board of the Environmental and Engineering Geophysical Society, and so that's kind of where my career has been. So, like I said, I'm excited for this webinar. It's the day after World Trenchless Day, but we're doing the encore anyway because people wanted to understand this technology and how it relates to utility locating. And you know, what we're going to do now is just jump right into it. Okay, so here's our journey, just to kind of recap. How does it work? Right? How does this technology work? How deep can it see? Right? Quote unquote, how deep can it see? And in order to understand how deep it can see, we're going to look at two things. We're going to look at antenna frequency, and we're going to look at the physical properties of materials, because those are the two things that drive how deep your GPR can see, and it drives then what your success rates are going to be like on any given project. So what kind of frequency you're using, and what are the materials that you're going to be surveying within, and will that allow you, will that be conducive to allowing your GPR to see deep enough or with enough clarity to identify your buried utilities. Finally, we're going to have a comparison with EM locators, see what the positives and negatives are of both of those, and then we'll have our Q&A session. So let's begin. How does it work? Here are several examples of ground penetrating radar units that are typical in locating buried utilities. Okay, now they look a little bit different from each other. The wheels are different sizes, the number of wheels, the antenna boxes are different colors, but each one of these things has two components that all GPR have. Okay, two components that all GPR have. Number one, a console. Number one, every single GPR is a console. Now, the one that I point out here is a little bit more like a computer, but on the other units that are shown, you know, you have a tough book or whatever the case may be. What the console does is it actually it tells the antenna, right, which is here, to send out the signal, and then it records the two-way travel time of that signal and the amplitude of its reflection, if there is some reflection below the ground surface. So the console, right, and then the antenna are the two components that every single GPR has in any circumstance. Typical for utility locating is they will have a wheel, and often now with a push cart, which allows you easier data collection. But the wheel, when you calibrate it, it tells you how far you've gone based on how many rotations the wheel has turned. And so it's a very accurate way to measure your distance and the locations of GPR. In addition now, though, you can use a GPS with your GPR, and it'll be able to give you coordinates for every single GPR data point. So this is the basics of what GPR look like. All right, now how does it sort of work? Let's take an example. Okay, here is a model of a GPR that, right, has your cart system, has your console, has your antenna. And what GPR does is it emits an electromagnetic wave into the subsurface. Now that wave is going to continue down into the subsurface and spread until the signal has completely dissipated. Now, if the signal was moving through vacuum space, it would go on forever. Right? If the signal was moving through vacuum space, it would go on forever. There's nothing inhibiting it. But when it's moving through soil, or it's moving through concrete, or it's moving through some other rock, or some other kind of medium, then eventually that signal will dissipate because the material that it's traveling through will absorb some of that energy. And some materials, it'll absorb it faster. Other materials, it'll absorb it slower. But that's exactly what happened. It puts out an electromagnetic pulse, a wave that travels through the subsurface. Now, if there is a target that you're looking for, or some sort of discontinuity in the subsurface, then some of that wave's energy will bounce off of that target or reflect off of that target, and some will continue on down into the subsurface. Now, how much is reflected back depends on how different the target is versus the material that the wave was traveling through. So in this case, if there's soil, right? It's traveling through soil, and it hits a target that's maybe made of metal. Those are two very different materials, and it may reflect most of the energy back, okay? So that's what happens is the signal reflects off of a discontinuity, and then at the surface, the GPR records the two-way travel time and the amplitude of the reflection, or how much of the signal was reflected back. So this is a very simplified model, right? Let's say, for example, you have a sewer pipe here, right? That purple circle is represents a sewer pipe. What would this look like in actual GPR data? Well, here's an example. Okay, here's an example of GPR data that I collected, very simplified conditions, where we were detecting a sewer pipe. And what you see here is a reflection off of the bottom of the asphalt, right? So it was actually in a parking lot, bottom of the asphalt. Some of the energy continues down, and then it reflects off of that sewer pipe, giving that signature hyperbolic reflection. Okay? By the time it got down there, some of that signal has already dissipated, right, or has been absorbed by the soil, but we still were able to get a mild signature, right, or reflection off of that sewer pipe. So this is very typical, right? This is a simplified model, but certainly typical of utility locating. Using GPR to locate something, and in this case, it was not metal. It didn't hold a current. It could not be located with an EM locator. It was actually a clay pipe embedded in clay, and we still saw it probably because of the air inside of the pipe. So when it transitioned from clay into that air, pocket inside of the pipe, the air-filled pipe, some of the energy reflected back to the ground surface, and we were able to see that with the ground penetrating radar. So that's kind of fundamentally how it works. So how deep can it see, right? How deep can it prospect? How deep, can your pipe be buried for your GPR to still identify? And the answer is, well, it depends. And it depends on two different things. Number one, it depends on the antenna frequency that you use. So frequencies have antennas will have different frequencies, and different frequencies will allow you to prospect deeper or more shallow. And it'll depend on the material properties that you are surveying within. So I'm going to take you back for a second to high school science class, and we're going to talk about some very basic characteristics of waves. And so waves have three main characteristics, we'll say. They have a wavelength, a period, and a frequency. A wavelength, a period, and a frequency. And this should be familiar then, right? This is a wave form. This purple wave has a period of 2 seconds. So it takes 2 seconds for the wave to complete a full cycle. The purple wave takes 2 seconds for the wave to complete a full cycle. Now this blue wave that came up next has a different period, right? It only takes the blue wave 1 second to complete a full cycle. Purple wave takes 2 seconds to complete a full cycle, which is its period, and the blue wave takes 1 second to complete its full cycle, right? So which is its period. So the question is, what is the frequency of each of these waves? And the way you calculate the frequency is 1 divided by the period. And so the T there stands for period. So what's the frequency of the purple wave? Well, if you did the basic calculation and you did 1 divided by 2, super simple math, then it equals 0.5, right? 1/2. Okay, 0.5 is the frequency of the purple wave. Next question, what's the frequency of the blue wave? Well, 1 divided by 1 is, you guessed it, 1. So the blue waves have a frequency of 1. So the final question in this sequence then is, which wave has a higher frequency? And I know it's really simple, and I know I'm driving this point home, but the reason that I'm doing it is because this is fundamental to understanding how deep your GPR can see, how deep it can prospect, how deep it can image in the subsurface. So, which one has a higher frequency? If you said the blue wave has a higher frequency than the purple wave, then you have the right answer. The blue wave does have a higher frequency than the purple wave. In fact, it has a frequency that's twice as high than the purple wave. This is critical because since there's a range of frequencies that GPR antenna have, and I'll show you sort of a general range here, you can understand how deep or how shallow GPR antenna can prospect. So this is the general range of what most GPR frequencies are, about 100 megahertz to 2000 megahertz. You do get GPR antenna that are below 100, even down to 15 or 12 and a half megahertz, which are very, very low frequency. And you do get GPR antenna up to 2600 megahertz, which is a very high frequency. Now, the lower frequencies, right, like the purple wave, for example, have longer wavelengths. Okay, the purple frequency, or the lower frequencies, like the purple wave we showed, have longer wavelengths. The higher frequencies, like 2000 megahertz, have shorter wavelengths. Higher frequencies equal shorter wavelengths. So, which can prospect deeper? The longer the wavelength, traditionally, the deeper your GPR can prospect. So a 100 megahertz antenna, for example, will be able to prospect much deeper than a 2000 megahertz antenna. A 100 megahertz antenna will see a buried utility that's buried deeper, right? More likely to see it than one that's 2000 megahertz. Now this range overlaps with some other electronic equipment. I'll give you some examples so you can understand kind of what other electronics overlap with GPR. And so number one, right, at the low end, 100 megahertz, FM radio, aviation communication, and older TVs send out signals that are in the range of low frequency GPR antenna. 500 megahertz, some more recent TVs are in that range. Again, these are now getting pretty old too, but nonetheless, UHF TVs are within that range. At 1000 megahertz, you get cell phones in the cellular band, okay, in the 800s, and medical equipment often emits frequencies in the low 900s. And then finally, at 2000, mobile phones, newer mobile phones with PCS bands emit frequencies of about 1800 to 2000. Now, most phones today are multi-frequency, and they'll have cellular band and they'll have PCS band. But the reason I show you this is generally the frequencies used in utility locating are between about 200 and 1000. Okay, generally, the frequencies that are used in utility locating are between about 200 and 1000. Those tend to be the most effective frequencies. What's important about this is if you have overlap from one of these other technologies, it can reduce the data quality of your survey. So for example, if you have a cell phone on while you're collecting data and your cell phone overlaps, if you have a 900 megahertz antenna, for example, and it overlaps with the frequency of your cellular band, that can create unwanted noise or unwanted background noise in your data set. If you're doing a locate on a hospital parking lot, then you have medical equipment that might be emitting electromagnetic waves, which are the kinds of waves emitted from GPR, at 900, right, at the low 900s. That can affect it, and you can get artificial reflections, events in your data that actually aren't even there. So you have to be careful of what's going on around you. This is a critical point. I always say be aware of what's going on around you and control what you can control. And while it's common sense, it's not always common practice. And in our, at LearnGPR.com, in our introductory course, GPR Basics, I actually have an entire module about this. That's how important it is, about the steps for successful GPR survey. And the first step is control what you can control. And so we talk about this, you know, at length in that course, because so much of what I see as failure to succeed in GPR surveys could have been avoided. Right? And so in this case, things like basic things like turning off your cell phone during your survey because it might interfere with your signal or add background noise is critical. So you can, so keep that in mind as you're doing your surveys. So here's a recap of antenna frequencies. The low frequencies between about 12.5 0.5 to 200 megahertz would be considered low. They have long wavelengths, and they can prospect deep, in some cases up to 150 feet deep. And so these tend to be used for geological and geophysical applications. On the other side of the spectrum, high frequency, 800 to about 2600 megahertz. These have shorter wavelengths, can only prospect very shallow. I can only see between, in the subsurface very shallow, sometimes as little as 12 inches, like a 2600 megahertz antenna, and are often used for concrete scanning and utility locating, kind of in that 800, 900, 1000 range. So between 200 and 800, you certainly have antennae that are often used in utility locating. Things that are very common are, for example, 300, 400, 500, or 250 megahertz antennas. So this is a summary kind of how they differ. So point number 2 then, that affects how deep your GPR can see, are the physical properties of the material that you're surveying in. The physical properties of the material that you're surveying in. And really what's important are a subset of properties that include the material's conductivity, its permittivity, and its permeability. And together, these are generally referred to as the dielectric constant of a material. The two that really affect the dielectric constant, or that affect the performance of GPR equipment are conductivity and permittivity. Okay, conductivity and permittivity. These are considered the electrical dielectric properties. Permeability is considered the magnetic dielectric property, and that often has a significantly smaller effect on your GPR survey. So conductivity and permittivity are the ones that really are the driving properties for your survey. Conductivity is generally related to how long your signal strength is going to be maintained, and permittivity is often related to how fast or how slow your wave is moving. Okay, so those are the two that are critical. And to sort of show you an example, let's get into two polar opposite materials and see how waves are affected within these materials. So I'm going to compare right now air and water. And while we're comparing air itself and water itself, most of the soils or materials you're going to be working within are really a function often of how much water is saturated in there, or how much air is in the material, right? What kind of porosity does it have, and are those pores filled with water or are they filled with air? So this is important, but we're going to take polar opposites just to drive the point home of how different materials can affect the performance of your GPR equipment. So here's a question. Which one of these materials is more electrically susceptible? Okay, which one of these materials is more electrically susceptible? Well, I'll give you a little story. Kind of help you understand this. You probably know it anyway, but when I was little and I was in the pool swimming and it started raining outside, my parents told me to get out of the pool when it started to lightning. Why did they tell me that, right? I responded to them. I said, I'm already wet. Okay, the rain's just going to get me more wet. And they told me it wasn't about the rain, it was about the lightning. They told me it was about the lightning because the water, right, attracted the energy. It attracted the electricity. It was highly electrically susceptible. And so if you picked water here, then that is the right answer, right? Then that's like 2 points for you. Okay, so water. So water is more electrically susceptible, which means then that water has a greater dielectric constant than, or a higher dielectric constant than air. Water's dielectric constant is 81, give or take. And water is the highest dielectric material, dielectric constant material of any naturally occurring material on Earth. There are metals that have been processed that have higher dielectric constants than water, but for naturally occurring materials, water at 81 is the highest dielectric constant that there is, that we know of. Air, on the other hand, is almost 1. It's almost 1. So what would 1 be, right? What kind of material would be 1 if you had vacuum space with nothing in it, no particles, no nothing? that would be equivalent to 1. Air, however, is 1.00053, give or take. And it's almost 1 because there are some particles in it that could, or that do, slightly hinder or slow down the speed of an electromagnetic wave as it's traveling through air compared to a vacuum. Okay? So what are the speeds of these two materials? Right? Which material does light travel through faster? Now, light, GPR does not emit light energy, but light is an electromagnetic wave, and GPR emits radio, right, electromagnetic radio waves. But in this case, which one does light travel through faster? If you picked air this time, then you're correct on this one. So in air, light travels at 299,700 kilometers per second. Water travels much slower in 225,000 kilometers per second. Now that difference is what makes light bend, right? The pathway of light bend when it hits water. So when you shine light into water or you put an object into water, it looks like the object is bent. Like if you want to freak some kids out or something at a party, you want to do a magic trick, right? Take like a straw, put it into water, and show them that the straw is now bent in the water. Is it really bent? No. What's happening is the light pathway is bending. And the reason it does that, it refracts off of that water-air interface because it changes speed. So whenever the electromagnetic wave changes speed, it will reflect or refract off of that, any given interface. And so it travels slower through water. Well, what does that mean? It means it travels slower through high dielectric materials, and high dielectric constant materials. How fast is the speed of light in a vacuum? 299,792 kilometers per second. So air, right? Light travels almost as fast through air as it does through a vacuum, right? And that is why the dielectric constant of air is almost 1. Okay, a vacuum is 1, air is almost 1. It's because the speed that light travels through it is almost the same. Water, on the other hand, is much slower, which means that lower dielectric constant materials, light travels faster. Higher dielectric constant materials, light travels slower. So to review, what is the relationship between wave velocity and dielectric values? I know I've made some pretty strong correlations here, but the real answer is it's complicated. Okay, it's complicated. But in general, I can give you some rules of thumb, okay? And here they are. Materials with high velocities have low dielectric constants. And in those low dielectric constants, usually the signal dissipates slower. So you usually have waves moving at rapid speeds and the signal strength holds up for longer time. That's ideal. So low dielectric constant materials are ideal, and I'll give you some examples of those in a second. But high velocities with slow dissipation rates allows the wave to continue down into the subsurface or into the material for longer periods of time at faster rate traveling speeds. On the other hand, materials with low velocities have high dielectric constants and the signal dissipates usually faster. You often have low dielectric constants with high conductivity, and so that's why you get faster dissipation of the signal or attenuation rates, where you have those those that are high dielectric constants, right, where the wave's moving slower, you get fast attenuation rates. So it's like a double negative, right? It's two bads for low dielectric constant materials. So things like wet clay, which is an example, waves are going to move slow through wet clay, and they're also the energy is going to be absorbed by that wet clay very fast. So you're only going to be able to prospect pretty shallow in wet clay. These are the general rules of thumb. Okay, low dielectric materials like in air, wave speeds are fast and wave signal holds up. High dielectric constants, generally like wet clay, for example, have low velocities with rapid signal attenuation, meaning that the wave doesn't hold up for too long. Now, what kind of things complicate this? We're not going to go over it here, but same in the GPR Basics course and the introductory course at LearnGPR.com. In our module about physical properties of materials, we have a whole section on what kind of things complicate these relationships. because there are a number of them. And so you can go over to learngpr.com and check those out. Here's a summary. Concrete and dry sand are examples of low dielectric constant materials, right? So here in concrete and sand, waves are moving fast. You get deep prospection and slow attenuation rate, so the signal holds on for longer. In high dielectric materials like wet clay or salt water, you get very slow moving waves. Slow moving waves, not slow moving waving. Slow moving waves. The waves prospect shallow, right? You can only see pretty shallow. And you get rapid attenuation rate. So the signal strength is going to dissipate quickly. Now, and you do get a clustering of the radar signal, just as an aside. Okay, so that's kind of the overview. Concrete and sand are low dielectric, which means that concrete and dry sand are ideal conditions. Salt water and wet clay, right, or beach salt, right? So if you're working on the beach, on the ocean, near the ocean, or you're working in wet clay, like where I work, for example, you're going to get those are high dielectric materials, and you're going to get non-ideal conditions. But here's a question that I get all the time: can you use GPR in wet clay? The answer is absolutely. I built my career on using it in wet clay. I do projects weekly where we get successful, survey, and locate targets in wet clay all the time. I had somebody the other day, however, tell me that they purchased 2 GPR and almost never or never bring them out because around where I live, there's a lot of clay. And it doesn't work in clay. It does work in clay. And I'm going to give you some examples in a moment, actually right next, that show the use of GPR within clay environments. Okay, so it just happened to be that way. I wasn't doing that on purpose to drive this point home, but it will drive the point home. So yes, you can use it in clay, but you have to understand the limitations in clay and understand the kinds of frequencies you can use to try to overcome those limitations. Okay, so we're going to get into a few examples. Here's example number 1. This, what you're looking at, is a profile, 30 meters long, of a survey, and I collected a number of profiles next to each other, and we're going to look at 2 that are 3 meters apart to compare them, and then we're going to look at it kind of top down from an aerial overview after we resampled it to create a depth slice, right, or an amplitude map is what it's called. And I'll show you those in a second. Now, within this data set, right, can you see any possible targets that might be utilities? And the answer is, of course you can. Right? Of course you can. And here are those possibilities. Okay, so here are those possibilities. Those are generally the buried hyperbola. Some may be metal. Some look like they may not be metal. Those over here, for example, with the multiples, appear to be metal. And those over here, right, appear to not be metal. Now, whether or not they're actually pipes or some buried utility is unclear at the moment. But there are definitely some candidates for possible utilities in this location. Okay? Okay, so let's look at 3 meters north of this data set. So this is a profile. This is like if you trenched into the ground and you looked at the side profile of your trench, this is what you'd see. Okay, so what does it look like 3 meters north? Here's what you get. Is it identical? Certainly not. Okay. Can you see some of the same exact targets? Yes, you can. Right. So here are the ones that you can see in this profile. Now, not all of them are the same, right? So in this case, you actually have 4 potential targets over here or more. This one holds up, but it's not exactly in the same place. So maybe it is a pipe that's moving in a certain direction. And you get a couple over here that hold up, but several that were in the A profile do not really show up or are hard to interpret in this B profile. And I'll put some question marks on them there. So it can be very difficult to understand what's going on below the surface just by taking profiles. However, one of the main benefits of GPR is that you can resample these data and look at them in 3 dimensions. And so what I did was I took all of these profiles, all of these, right, non-invasive trenches that I collected and put them together. And so I was able to look at them in slices, kind of 10 centimeters below the surface, 20 centimeters below the surface, 30 centimeters, and so on, to understand if there's any patterning within these data. And this is what we came up with, okay? So this is the GPR data. It's a slice map that's just about, maybe a foot below the surface. And you can clearly see several patterns of reflections, okay? And these are interpreted as utilities, buried utilities, okay? They go in a variety of different directions. Most are linear, some curve, but these are interpreted as utilities. Now, what's really neat about this is that the ones that are extending beyond the boundary of the survey actually have some variation in the color of the vegetation from the aerial map. You can see these extended, right? You can sort of interpolate those right here. So it looks like we were spot on. And they were able to identify a number of utilities in this area that were buried, many of these not being metal and could not have been detected with traditional EM locating equipment. So ones that do not hold a current could not have been detected with that. But in this case, we were able to get a three-dimensional view of what's below the surface here. We found a number of buried utilities, whether they're water pipes or power or what have you. And we're able to map those in great detail in this area. And as well, we're able to see, which to me is very cool, the extrapolation of those from variation in the vegetation color right on the Google Earth map. Just one example of locating utilities, and here's kind of what it would look like both in profile view as well as top-down and three-dimensional view as a time slice or a depth slice. Here's another example. So what you see here in this grayscale map is conductivity data. It's electromagnetic induction data, and what you see is almost no variation in the subsurface here in its conductance. Right, in the ease or difficulty to induce a current, it is difficult to induce a current across this whole thing. And especially so right over the sidewalk where you see where you see a conductive low, right, with conductive highs on the sides of the sidewalk because you get pooling of water on the side of that concrete. But this is the boundary then where we did the GPR survey. So according to the electromagnetic induction survey, there does not appear to be any targets below the surface. With the GPR survey, however, here are some examples of those slices into the subsurface. And you can see one very compelling candidate for a pipe that's buried about 1.5 feet below the surface. And that one is on your left. Should be on your left, certainly on my left. And that's this linear reflector right here. By the time you get to 1 meter deep, it's gone. Can't really see it. This may help you get some indication of pipe diameter as well. But we were able to see this here, and it's probably a ceramic drainage system is what we interpreted it as. Obviously, it doesn't hold any sort of current, or else it would have been identified by the conductivity meter. And so it doesn't hold current. It's clearly linear. It's going down slope into a stream, and so it's probably a drainage system. Okay, here's one other example. Okay, one other example of data. This is not technically utility locating, but it's going to be underground storage tanks. So these are 2 underground storage tanks, and this relates to certainly trenchless technology and the kinds of work that subsurface utility engineers do. And so as this was in support of World Trenchless Day, I'm going to go ahead and go over this example as well. And so what we were able to do here, this is at a gas station, clay matrix, by the way. So does it work in clay? You're darn right it works in clay matrix, and we can actually see a lot of what's going on here. So first of all, we can clearly see these 2 underground storage tanks buried about 80 centimeters deep. And those are those 2 large hyperbolic reflections over there. What else were we able to see? We were able to see the reinforcing steel in the concrete above the rebar. I'm sorry, above the USTs, right? We were able to see the rebar above the USTs. But even cooler, I think, is that you can see very clearly the edge of the excavated trench that the two underground storage tanks were buried in. On the left-hand side, you get a very different amplitude response compared to the right-hand side, and that is a clear indicator of a trench. There's some other things going on here as well. Okay, so this right here, this reflection, is what we interpreted as an air wave. And so by understanding what's around you, I'll say it again, right? Understanding what's around you and understanding how the waves behave, we were able to recognize that this reflection actually was something from the ground surface that our GPR was moving towards. And as we moved closer and closer to it, the GPR wave moves, it spreads out. And so it spreads out across the ground as well. And as it spreads out across the ground and we're moving closer and closer to it, it's reflecting off of that object back to our GPR, but it's taking less and less time, which is why it looks, right, less and less deep. It's ascending towards the ground surface as you move from left to right, because we were getting closer and closer to that object. But if we didn't know, right, that was how GPR waves behave, we wouldn't be able to understand that was a ground surface reflection. So that is the ground surface, not the side of a trench wall. But in addition, and I didn't mark it here, but this is likely a pipe going into the USTs that's pumping the fuel right from the USTs to actual gas pumps. Okay, so this is at a gas station. This is probably the pipe, probably fiberglass, that is transferring the fuel. So here's kind of another example of ground penetrating radar data for trenchless technology and for understanding, its ability to locate buried infrastructure, both utilities and storage tanks alike. Comparison of GPR and EM locators. Okay, we're going to kind of finish off here with a brief comparison of these, and we see the kind of the strengths and weaknesses of both of them. So let's go through a series of questions. Which, we talk about, what about the data collection speed? Okay, which is faster, which is slower? Well, EM locators are much faster in collecting data than GPR. And for super simplified projects that can, on things that can hold a current, they're great. They're phenomenal. It's so much faster than collecting GPR data. Okay, certainly than collecting a GPR grid, although you don't always have to have a GPR grid collected. And you can check out some of our videos on YouTube where I actually talk about that. I talk about grids versus GPS systems versus nothing, versus just literally walking around and marking targets. I talk about those three on our YouTube channel. But data collection speed for GPR is generally slow compared to EM locators. Okay, so that's sort of a limitation of GPR and a very positive thing about EM locators. In addition, you can actually link that on for EM locators to a specific utility and trace it out, and typically get that utility specifically located so you know what it is. So the necessary conditions for using GPR versus EM locators. Well, for GPR, you have to have pretty good conditions, but you have to have really nicely manicured surfaces. So on concrete, it works really well. On asphalt, it works really well. On cut grass, it works really well. It can work well in higher, taller grass. I've certainly done that before. And you can get into forests that aren't too dense, but it really becomes limited in situations where there's a lot of obstructions on the ground surface. Unlike EM locators, you can work anywhere with the EM locator. It doesn't matter, right? I mean, you can work literally anywhere, including in highly dense forests. Maneuverability is very poor with GPR in general, especially with cart systems, but there are ways to combat that a little bit. And so you can hook a GPS unit to it, so you can kind of just maneuver around how you want. And you can actually take your antenna off of a cart and just pull it, and that sometimes makes it easier to maneuver your antenna. And what you might do is put a survey wheel or a GPS right on it and just drag it instead of pushing a big, clumpy cart around. So overall, it's poor, or certainly, the maneuverability is worse than EM locators, where it's great. You can walk anywhere you want, however you want, right? I mean, you can dance your way down the street if you feel like it. It doesn't matter. You can be in, maybe you want to save that, but if you're in the woods alone, you can locate and dance in the woods with your EM locator. is highly maneuverable. Okay, it's excellent for maneuverability. Costs. GPR currently costs more than EM locators, and locators may cost a couple $1,000s, $3,000, $5,000. GPR can cost anywhere between $12,000 and $36,000, and it's obviously a higher price technology as of right now, and probably will stay. But the costs are coming down significantly for GPR. What can it locate? Here's where GPR really shines. GPR can locate any material potentially, as long as that material has a contrast with the material that it's embedded in. And in many cases, you actually don't need to locate the material you're looking for. So take pipes, for example. Often you don't need to locate the pipe. I have located clay pipes embedded in clay soils. And there's very little difference between the clay pipe and the clay soil. It didn't matter. I was able to locate the air within inside the pipe. Sometimes I get people telling me, I can't locate the pipe because it's too deep for my radar and the conditions are too poor. I say to them, can you see 2 feet within the surface, even if your pipe might be 8 feet below the ground surface? They say, sure, I can see 2 feet within the surface. Well, then can you see the excavation trench where the pipe was? Okay. As it gets more and more trenchless, that may be more and more difficult to see. But certainly with hundreds of years of embedding utilities, 100 years plus embedding utilities, into the ground using trenching and excavation, you should be able to see those trenches. You might not even have to see your pipe, just see the trench or see the material inside the pipe, whether it's sewage, water, air, whatever. Accuracy. Again, GPR shines here. So they're extremely accurate in all three, the X, Y, and Z dimensions for GPR. So you can get, as long as you know how fast the wave is moving and you know its two-way travel time to where it reflected off of your pipe, your utility, you can use time, and speed to get distance, or depth in this case. So it's, and then further, there's no, well, it's plus or minus, here, 18 inches, as far as horizontal accuracy, right? Once you're over the peak of that hyperbola, you are on the utility. There is no plus or minus. With EM locators, you get a range. You get a range of X, Y, and Z dimensions. So that's one of the limitations of EM locators. And finally, data visualization, right? You can view GPR data as one dimension, as a single trace, right where you're standing. 2 dimensions, like a profile, like I've shown you throughout this webinar, or 3 dimensions, where you can actually resample your 2D data and look at it top down as slice maps into the subsurface to see those those patterns, like I showed you, those linear patterns and sort of curving patterns, which are no doubt utilities. EM locators, traditionally, there's no data that you can visualize. Sorry, it was a mouthful. You can visualize, but you can take GPS coordinates as you're locating them, and then just plot that on, an aerial photograph, or in CAD, AutoCAD, or GIS, or something like that. So using GPS, in conjunction with EM locators is very helpful, but still, you can actually, you generally don't visualize the actual data. But with GPR data, you can visualize all of them. Though that's the same thing, changing a little bit for EM locators. Some companies now are combining GPR with EM locating to give you sort of a much deeper and richer data set. And that kind of brings me to my final point, which is that, is it an either or, right? GPR versus EM locator? It's not a versus kind of thing, right? What you can see here is that they both have strengths and they both have weaknesses. And really, it's about using the right tool for the right job, or more appropriately, using both tools for as many jobs as you possibly can. Because even if you locate most of your utilities or all of your utilities with an EM locator, what if there's something that doesn't hold a current and you couldn't locate? GPR can help there. What if you want complete accuracy because every inch counts on your construction project, and you want to make sure that you can get within a certain inch of a utility? You don't want plus or minus 18 inches. Getting the exact location and possibly even the dimensions of that pipe using GPR can be very useful. So I think that they're complementary. These instruments are complementary and should be used in conjunction as much as possible, because you will get a richer data set. Even if you just take it off your truck, your GPR and go over your markings already to get a little bit better accuracy without even conducting a whole grid survey, that's even an added benefit, right, for your project. So use the two of them together when you can. All right, so as a conclusion, right, even though World Trenchless Day was yesterday, still check out their website, worldtrenchlessday.org, to see upcoming events for next year and get on board. It was a wonderful thing they did, a fantastic initiative to get a lot of people on, around the world speaking the same message, which is preservation, which is safety, and go to their website for more of that. Visit LearnGPR.com and sign up to receive free training videos every single Monday in your inbox. We produce instructional videos for free on a different topic every single week, and we will send that to you. They're usually about 3 to 10 minutes long, depending on the topic, and we'll send you one of those every single week so you can continue your education. And finally, I'm not going to beat this to death and give you all kind of sales pitch, but if you're interested in additional training, contact me directly. You can contact me at dbigman@bigmangeophysical.com, and if you go in the comments below for this video, then my email is right there. And email me with your information and where you're from, and I'll call you back. Right? I'll call you. Give me your phone number. I'll call you back, and we'll set up a time that's convenient for us to speak. And I can show you kind of what training options are available. We have a variety of training options, to very short webinars, to more intensive online courses, to on-site multi-day hands-on trainings. And so we can talk about that. And if what we have isn't right for you, I'll still gear you in the right direction. If you don't have a radar right now and you're thinking about purchasing one, I'm happy to talk to you for 10 minutes anyway, to maybe give you some guidance on the most appropriate system for your purposes. So I'll do whatever I can to help you and educate you. Our goal is to increase the awareness of this technology, educate people on this technology, and advocate across the world for its use in all disciplines that can benefit from it. So we're going to go ahead and take some questions now. Thank you so much for staying on the webinar. I hope you got something out of it. And subscribe right now to this YouTube channel. If you have not subscribed yet, subscribe to this YouTube channel, and you will get notified when we have videos or other free webinars like this, which we're going to start doing more regularly on a bunch of different topics. And so let me help you. Help me help you, right, by subscribing to YouTube now, and like this video if you thought that it was useful.